magnetic field. Describe its subsequent path if it enters perpendicular to the field. So this is the first one, this plane shown here that sits perpendicular to the field. So the key idea here is that the velocity is going to be perpendicular to the flux density vector. So when we come to use Fleming's left-hand rule, the velocity of the particle and the field are always at 90 degrees to each other. This means we get a force that acts at 90 degrees to both. If we have a force that always acts at 90 degrees to the velocity, we get circular motion. So circular motion perpendicular to the field. Second one, if it enters at a slight angle to the field, so that's shown by this slice here, it's coming in. Now when it arrives, we can picture its velocity as having two components. This velocity has a component that is perpendicular to the field and a component that is parallel to the field. So the component that's perpendicular to the field, well, that works the same as in A. It's going to cause circular motion in a plane that's perpendicular to the field, but the particle also retains this velocity that is parallel to the field. So we would expect this thing to follow a spiral that comes out through the plane, keeping the initial velocity that was parallel to the field at all points. So we'd expect this to form a spiral in the field. So this component, so this causes a force at 90 degrees to the magnetic field, and therefore an acceleration to make it go in a circle, whereas this one is not affected by the magnetic force, so it remains unchanged. The component parallel to the field is unaffected, so the motion is a spiral through the field. This is effectively what we use inside things like the nuclear fusion reactors. So we maintain, we're able to make plasma float inside a nuclear fusion reactor by having the charged particles spiral along magnetic field lines. So it's a very similar principle, and inside a nuclear fusion reactor we have to carefully shape the magnetic field so that the charged particles can continue to spiral along these magnetic field lines without ever bumping into the sides. If they bumped into the sides, they'd lose all their energy and the fusion would stop. And then C, if it's parallel to the field, well, it experiences no force, so no magnetic force caused on it. So therefore it travels in a straight line. Straight line, completely unaffected by the presence of the field.